morning, everyone. So we're going to continue our journey into Chapter 8, looking at types of chemical reactions. So previously we looked at chemical reactions that where we identified different types of reactions. We learned how to predict solubility and write dissociation equations. So in this latter part of the chapter, we're going to look at writing net ionic equations for double replacement reactions. So we already know how to predict a product of a reaction. So if we're looking to predict a product of a reaction, we know what to do. But in those reactions, in those equations, we're seeing everything that's happening. So what if we're only interested in seeing the essential parts of the reaction, giving a short, concise message about what's happening in the chemical reaction? So in a standard equation, we see everything. So here's our standard chemical equation where we're reacting silver nitrate with sodium hydroxide, affording silver hydroxide and sodium nitrate. What if we only show the ions and what's happening in solution? Because this is an aqueous solution, and these reactions all occur in an aqueous environment. So what would we do here? We would simply ionize all the compounds that are soluble, and we would then leave all of the compounds that are insoluble as undissolvable materials, as unionized compounds. So for example, silver hydroxide here, that compound does not ionize, so we don't show it as ions in the product. Okay. However, when we look at the other compounds like sodium nitrate and silver nitrate and sodium hydroxide, all of these compounds are ionizable. So therefore they get separated into their respective ions. This equation here, where we're showing all of the ions that are happening except for the ones that are insoluble, is referred to as what we call the Ionic equation. So we take our Ionic equation, and what if we were to simply simplify this? Let's simplify what happens and only look at the components that are part of the chemical reaction, that result in the net chemical reaction. So let's examine what happens. So which ones are part of the chemical reaction? Well, we have the silver ion and the hydroxide ion. Those for sure are part of the chemical reaction. So let's eliminate everything else that does not form a new compound. So how would we do that? We would begin with our ions that we have, and we'd eliminate nitrate on both sides because nitrate is not in a new compound per se. It's not in an insoluble material. And then sodium ions are also on both sides. These are referred to as what we call spectator ions because they're found on both sides of the equation. So spectator ions are simply ions that don't participate in the net reaction that's occurring. So that leaves us with the following equation. Silver ions plus hydroxide ions make silver hydroxide solid. That's what this net ionic equation is showing us, where there's the net reaction overall. We're only interested in what happens with forming the new solid product that can be separated. So we know for sure that we have something called a molecular equation where we're looking to see what happens at the molecular level. We're looking at all of the large components. Silver nitrate as a compound, sodium hydroxide as a compound, produces two other compounds, one soluble and one insoluble. Then we have the ionic equation that shows us only what happens at the ionic level and only shows us what happens with ionizable materials. The materials that are not soluble, again, can't emphasize that enough, they do not ionize. And finally, here's our net ionic equation where there are no spectator ions. We've eliminated all ions that are found on both sides of the equation. So let's pause here for a second where you can do some practice of writing ionic and net ionic equations. So here are three equations. The first one we've already done together, but I'll go over one more time. And the latter two equations are ones that I'm going to give you an opportunity to pause. So here's a good time to pause the video, attempt the two problems at least on your own, and then replay the video for the answers. So let's look at this in a little bit more detail, the silver nitrate reaction with sodium hydroxide forming silver hydroxide and sodium nitrate. We've looked at this already and we know that this is the ionic equation that's formed. So how does that happen? Let's go review that for a minute to make sure that we know how the solubility aspect is happening. So we know that silver, here this silver compound, silver nitrate. So from table E we know that nitrate has a -1 charge. So therefore if silver and nitrate have a -1 charge and there's only one silver for every one nitrate and there's no leading coefficient here, we're going to end up with Ag+. And don't forget to indicate aqueous next to all species that are soluble. So that's how we know how silver is going to ionize and how many ions are going to form in solution. The same goes for sodium hydroxide. We know that sodium has a +1 charge because it is in group 1. And if we look at table E, we know that hydroxide has a -1 charge. Again, putting aqueous here. And we know for sure that silver hydroxide is indicated as a solid and it's insoluble. Based on the solubility rules that we've already studied, we know that all silver compounds except acetate and nitrate are insoluble. And then we have sodium nitrate, and again, this is a soluble compound for two reasons. One, it's indicated here by aqueous. And also, if we take a look, this is both a group 1 compound and a nitrate. So all nitrates and all group 1 compounds are soluble. And again, sodium is +1, nitrate is -1, and we know that from the other side. So the ratio stays the same. So when we look at now our ionic equation, and we eliminate spectator ions, we eliminate nitrate because it's found on both sides, we'll eliminate the sodium, and we're left with silver hydroxide. Silver ions plus hydroxide ions give us silver hydroxide. So let's look at the copper reaction in this case. Now this is a little bit more complex reaction because for the balanced chemical equation, there are a number of coefficients and there are also subscripts that we have to take into account when we are showing the ionization process. So let's look at the net ionic reaction and then see how we get to the net ionic equation from initially. How do I get to this answer? So in this situation, I have copper nitrate. We already know from table E, nitrate is -1. However, there's two nitrates here in this process, in this compound, which means that their copper must be a +2. Now, what's also important is for us to note that there's a leading coefficient of 3, and there's also subscripts. So the leading coefficient must be distributed to each of the different components and that's happening. So here we have 3 copper nitrate molecules. That means there are 3 copper ions that will form. So the 3 leading in front of the copper, that's down here. Now for nitrate, we see that there are 3 copper nitrate molecules that come into play. Now if there are 3 copper nitrate molecules that are required for this reaction, and each copper nitrate molecule brings 2 nitrates together, we're going to take the 2 from the subscript and multiply it by the leading coefficient to get 6 nitrate ions. That's down here. So that's where the 6 comes from for the balancing segment for the coefficient in the ionic equation. And we do the same for ammonium phosphate. So we look at ammonium phosphate and we see, well, ammonium has, there's a leading coefficient of 2, and we know that ammonium has a +1 charge from table E, and phosphate has a -3 charge. Okay, so what about the leading coefficients? So here, 2 molecules of ammonium phosphate are required for this reaction. Therefore, 2 molecules, and in each molecule, 3 ammonium ions come present. So 2 times 3 is 6. So we get 6 ammonium ions. And then we get 2 phosphate ions here, because there's only 1 phosphate ion per molecule, and there's 2 molecules, so therefore there's 2 phosphate ions. Looking on the other side, we see that there are 6 ammonium nitrate molecules that are needed for this reaction. There is no subscript at the bottom here. We know that NH4 is +1, and NO3 is -1. And there's a leading coefficient of 6 that's distributed to each of these. So it's very straightforward. Now there's one thing to recognize here right away, is that once you have a balanced molecular equation or chemical equation, and you distribute all of your coefficients with your subscripts correctly, your net ionic equation, your ionic and net ionic equation will balance themselves if it's done correctly. So here, if you take a look, we have 6 ammonium ion, 6 ammonium ion, 6 nitrate ion, 6 nitrate ion. And then finally, we're left with just the copper phosphate. And if we take a look, those atoms also balance themselves. 3 copper atoms, 3 copper atoms. 2 phosphate molecules, 2 phosphate molecules. Okay. So let's eliminate now our spectator ions. We get rid of nitrate on both sides. We get rid of ammonium on both sides. And we're left with copper 2 ions and phosphate ions to give us copper phosphate solid. And finally, let's look at the ammonium, sodium nitrate and ammonium chloride reaction, producing sodium chloride and ammonium nitrate. Now, one of the things to note here right away is that based on solubility rules, we can quickly predict that there's going to be no insoluble product. So what does that mean? If there's no insoluble product, it means that all of the ions are in solution both in the product and in the reactant. So what could potentially happen now in terms of an actual equation, a net ionic equation? If we take a look, all of our ions are spectator ions. They're found on both sides. There's not a single ion that's not found on both sides. So therefore, this process, all spectator ions are removed. There's no net ionic equation. It means that there is no chemical reaction here because there's no new substance produced. So that means if I simply mix all of these together, that I have the potential to get all sorts of mixtures of salts if I were to remove water at the end. So these are all in an aqueous environment. If I were to remove the water, I could potentially isolate salts and separate salts that include sodium nitrate. I could get a compound ammonium chloride. These are all the possible salt forms that I could get, because if I remove the water, we don't know what else is happening. And then we also have our original compounds, which were sodium chloride and ammonium nitrate. And that's it for today.